Modern data centers function as the primary engines of the global digital economy and the foundation of national security. Wireless digital experiences, from financial transactions to AI prompts, rely on thousands of acres of heavily guarded concrete, metal servers, and industrial cooling towers. This table summarizes the economic impact of data center development, showing how these facilities act as multipliers for their host regions. An initial direct investment of $1.1 billion generates a total economic output of $2.5 billion during the construction phase. These facilities support critical infrastructure, ranging from regional banking networks to military surveillance systems. Yet the physical mechanisms operating inside these windowless buildings remain largely hidden. To understand modern geopolitical power and digital sovereignty, we must dissect the precise architectural, thermal, and network engineering that keeps these facilities alive. A data center is split into two zones: the outer perimeter, or gray space, which houses support systems, and the white space, where the active IT equipment resides. The white space is populated with compute resources, including rack and blade servers that house central processing units and parallel processing GPUs. Directly adjacent to these processors is the data storage layer, utilizing hard disk drives for bulk archival and solid-state drives for immediate retrieval. Early deployment models were inefficient, often locking one physical server to a single application and leaving much of the processing capacity idle. Modern facilities use a software layer called the hypervisor to abstract physical hardware, allowing multiple independent virtual machines to operate simultaneously on a single server. Virtualization allows data centers to pool their computing resources and dynamically allocate them based on demand, reducing the physical footprint required for the facility. Raw physical hardware requires this virtualization layer to orchestrate and divide its processing power at scale. Inside the white space, servers and storage arrays must constantly communicate, generating a massive volume of internal data transfer, known as east-west traffic. Legacy networks relied on a three-tier model, but in hyperscale environments, data packets bottleneck at the middle distribution layer, creating severe latency. Modern facilities solve this using a leaf spine or closed topology, which flattens the network architecture to guarantee an equal distance between any two nodes. In this topology, every single access layer leaf switch must connect physically to every single core layer spine switch. This dense web enables equal-cost multipath routing, giving data packets multiple, equally fast alternative routes to bypass congestion instantly. The result is a non-blocking architecture capable of transfer speeds up to 800 gigabits per second. This routing topology allows thousands of individual GPUs to act together as a single, unified supercomputer, providing the architecture required to train artificial intelligence. Keeping a localized supercomputer operational requires absolute stability, as unexpected downtime in a hyperscale facility incurs massive financial and operational costs. Protection begins with dual power feeds from separate utility grid substations, feeding directly into the facility's main electrical switchgear. If the utility grid fails, an uninterruptible power supply provides instant battery backup, preventing even a microsecond of power loss to the IT equipment. These batteries hold the load until on-site diesel generators engage, restoring long-term stability with enough fuel storage to run the entire facility autonomously for up to 72 hours. High-density computing generates immense heat, requiring precise computer room air conditioners and hot-cold aisle containment to protect hardware from thermal failure. The Uptime Institute's Tier 4 rating indicates a fully fault-tolerant facility where any single equipment or path failure will not impact active operations. Designing a modern data center is an exercise in risk mitigation and thermodynamic control to ensure the digital environment never fails. Once data is processed, it must leave the server rack to reach a global end user via outbound transit known as north-south traffic. Load balancers at the network's edge manage this traffic, distributing incoming global requests evenly to prevent any single server from becoming overburdened. Data packets then move through perimeter firewalls, where security protocols inspect the traffic and verify credentials before granting entry or exit. Exiting the building requires a transition from internal multi-mode fiber to external single-mode fiber. Single-mode fiber uses microscopic strands of glass to shoot data as light pulses at 200,000 kilometers per second across oceans and continents. This perimeter, the load balancer, the firewall, and the fiber connection, bridges the highly controlled local environment with the global internet. The immense capital required to install UPS systems and leaf spine switches makes these facilities massive economic anchors for their host communities. This complete economic impact summary reveals that data centers require limited staffing, but generate staggering recurring tax revenue for local municipalities. State and local collections, detailed here, provide the recurring tax revenue used to fund regional infrastructure and schools. Beyond local economics, military intelligence, surveillance, and reconnaissance networks rely heavily on civilian hyperscale infrastructure to process real-time global data. Because a single facility outage can degrade satellite intelligence or cripple combat power, data centers are now legally classified as critical defense infrastructure. To protect these strategic hubs, regulatory bodies strictly block foreign adversaries from owning or accessing them. The classification of data centers as restricted defense assets signifies that physical uptime is now a prerequisite for national stability. Data center development remains concentrated in North America and Western Europe, tracking with established capital investment and power grids. Across much of the global south, hyperscale infrastructure is almost non-existent, creating a digital divide where entire continents lack localized computing power. This disparity highlights the reality of digital sovereignty, a nation's capacity to host and process its own data securely within its own borders. As artificial intelligence scales, nations unable to supply the power, cooling, and network engineering required for these facilities will face long-term economic subordination. Despite the misleading name, the cloud is actually a massive physical infrastructure built entirely from concrete, copper cables, and glass fibers. Managing this thermodynamic and topological bedrock is the final requirement for a nation to maintain its technological autonomy.